We've talked about linear functions that are lines on a graph that look like these. This black line, red line, and blue line are all linear functions. Now we're going to talk about nonlinear functions. Anything with a curve is a nonlinear function. It might look like this. It might look like this. It might even look like this. These are all sketches of nonlinear functions that of the kind we're going to talk about eventually throughout the year. Anytime it changes direction, essentially, it's not one straight line. Whether it's a V shape or a U shape or something more akin to an S shape, these are all nonlinear functions. Let's look at an example. Let's think about some information like the area of a square. If the square has one block on its edge, it has an area of 1. If it has 2 squares on its edge, then it has an area of 4. If it has 3 squares on its edge, it has an area of 9. Okay? So these are the number of squares, the number of boxes on the edge of the square, and this is the area of the square. Let me show you on this grid over here what I'm talking about. If we etch out 3 squares on the edge of our square, and then we finish off our square, we end up with a square with an area of 9 smaller squares, 9 1-square units. Or if we have a square of 4 on either side, 1, 2, 3, 4, 1, 2, 3, 4, we end up with a square area of 16. Let's graph this function. Let's graph the function that represents this distribution. So 1, 1, that's right here. 2, 4, that's right here. 3, 9, 7, 8, 9, that's going to be way up here somewhere. And you'll notice that this ends up being, by the way, if it has 0, what's its sides going to be? The sides are going to be 0. The area is going to be 0. Okay? So what you'll notice is that this ends up doing this. It takes this big turn, and it has this big curve to it. This is a non-linear function. Okay? And one of the ways you can see is that there's not a common difference as you go through, right? If you go 1 to 2, 2 to 3, 3 to 4, you're increasing by 1. But if you go 1 to 4, you're increasing by 3. If you go 4 to 5, you're increasing by 5. If you go 9 to 16, you're increasing by 7. Okay, there's not this common difference. This is not a linear function. Graphing is actually the easiest way to determine whether a function is linear or non-linear. When we graphed this function, it was obvious that it was non-linear because it was curving. Perhaps if we graphed another function and the graph looked something like this, you would say, oh, that's a linear function. So when you're looking to figure out whether a function is linear or non-linear, typically taking the data and just graphing it is the easiest way to determine whether it's linear or not linear. Here we've got some data. It's a nonlinear function, and we want to figure out what nonlinear function it is. So let's look at this first set of data, 1, 2. What kind of functions would produce 2 if I plugged in 1? Well, y equals x plus 1 would certainly do it. Y equals 2 times x would certainly do it. Also, one you might not have thought of is y equals 2 to the x power would also do it. Okay. So that works for the first point, all 3 of those functions. But for a function to be working for all the data, it has to work for all of the points. So now let's look at our second point, 2, 4. And let's look at our possible functions. 4 does not equal 2 plus 1. That one's been eliminated. 4 equals 2 times 2. 4 also equals 2 to the second power. Those are still in play. Let's look at our third point. 8 does not equal 2 times 3. 8 does equal 2 to the third power. Here's the function for this data. So that's sort of a try, check, and revise way of coming across what the nonlinear function is. Generally, in this section, you're going to be dealing with simple nonlinear functions. Ones like y equals 2 to the x, possibly y equals x squared, or even y equals x cubed are all options that you might come across in this section. So be aware, and you want to sort of have an idea of what the data for these functions look like. And if you're not sure, go ahead and make a input-output tree. So x, y, and let's look at what the data for this function would look like. If we plug in 1, we get 1. If we plug in 2, we get 4. If we plug in 3, we get 9. Hey, we saw this function earlier, right, when we were dealing with the square and the sides of the square versus the area of the square. That's actually why this is called x squared. Let's do the same thing with x cubed just to see what the data would look like if we plugged in and solved. So if you plug in 1 to x cubed, 1 cubed is still 1. If you plug in 2, what's 2 to the third power? 8. If you plugged in 3, what's 3 to the third power? 27. And that's what the data looks like when you have y equals x to the third power. The only changes you might see is when they start adding on constants too. So if this were not 1 but 2, let's make another variable y2, okay? If this were 2, 9, and 28, your function might be x cubed plus 1.